Hi everyone, welcome to week 10 of Stat 100. I hope you guys are doing well this week. I know it's been kind of a crazy semester with everything going on, but I wanted to check in and make sure that everything is okay. So if you guys have any questions, you can always send me an email or come to our office hours. I'm there most of the time if you want to chat. Your grades are currently updated in Compass. So if you want to know what your current grade is, double check on Compass and you will be able to see on our calendar that there's still a bunch more extra credit left in the class. So if you're concerned about your grade, the best thing to do right now is just to do all of the remaining extra credits. So all the remaining pre-lectures and surveys. And then, as I've said a bunch of times, I do drop your 3 lowest homework assignments at the end of the semester. So if you miss an assignment, not a big deal. I'm actually thinking for this semester, I'm going to go ahead and say I'm going to drop 4 of them. So instead of 3, let's just go ahead and say 4. With everything being online, I know you guys have a lot of things going on in your lives. So hopefully that helps. I know it's only one extra one, but I'll drop your 4 lowest homework assignments. So that means you can basically miss 4 without penalty. So hopefully that helps. I hope you guys have a great week this week. And like I said, if you need anything, let me know. So here comes some more random variables. Bye.
We're going to start right where we left off, which was talking about expected value and standard error. So the last page we did was page 131 in the notebook. And this is good. We are right on track for exactly where we need to be today. And we have pretty much covered all of the expected value and standard error formulas that I'm going to expect you guys to know. So Stat 100, it says on our syllabus, there aren't any formula sheets on any of the exams, but really you guys need to know, here, let's write them down. Maybe we should do that to have all of them in the same place. So I'm going to find, there's got to be some blank page somewhere. Here we go. I'm just going to use this gray page. Exam 3 formulas. So it seems like a lot, but really they're all kind of related. So the very first thing we talked about was expected value and standard error, right? We looked at sums, we looked at averages, and then we looked at percents. So for sums, we said the expected value of the sum is n times the average of the box. Right, that was the first one. And then the expected value is great and all, but we like to give a range instead of an exact number. So the next thing was the standard error for the sum, which was the square root of n times the SD of the box. So those were for sums. And then the next thing we talked about were averages and percents. And these weren't as complex. We said the expected value of the average, what would I expect the average of the number of tickets? If I draw n times out of a box and calculate the average of my tickets, what do I expect? Well, that's just the average of the box. So the expected value of the average is just the average. And then, hold on, I'm going to switch mics. This one's being not good. Please work. Hello. Nope, not working. Let's turn it up. Maybe that's okay. Now it's working. Test. All right. I think this one's a little bit better. Dang it, maybe not. Oh, I'm just going to leave it alone. Okay, so anyway, let's finish these. So expected value of the average, we just have to remember it's the average, not anything too complicated. And then the standard error for the average is like the standard error for the sum, but it's the SD of the box divided by the square root of n. So a little bit different, but still has SD, still has square root of n. And then for percents, they're basically the same as averages. The expected value for the percent is just the percent in box. So like if you're looking at the expected value for the percent of ones, you would look at, okay, how many ones are in the box? Are there 25% ones? Are there 50% ones? What's going on? And you want to put that in percent form. So these two are easy to remember. Expected value, the average is the average. Expected value, the percent is the percent. And then the standard error for the average and percent are basically the same, standard error for the percent, except the percent one we want in percent. So I'm going to multiply it by 100. So this is SD of the box over square root of n times 100. So these are kind of all related. Averages and percents. Basically, percents are just averages in percent form. So those are the 6. Yeah, there's 6 of them that we learned. And then there was one more that we talked about during the last class. And I said, if your box has 2 types of tickets, we can use this SD shortcut formula. Which is just basically taking, so it's the absolute value of the numbers on the ticket. So A minus B, those are the numbers on the ticket, so like 1 minus 0, and then times the square root of the fraction of A tickets times the fraction of B tickets. And then the fractions, if you want to put the fractions in percents, that's totally fine too. Or decimals, I guess. So like you could put 1/2 times 1/2 in here if you have half ones, half zeros, or you could put 0.5 times 0.5. Either way, you get the same exact answer. So these are the 7 formulas to know for exam 3. And like I said, these 2 are basically the same. These 2 are basically the same. These ones are kind of weird. Those are the only ones that are drastically different, I guess, with the multiplying instead of dividing. So those are there. I'm just going to leave those there for a second. And then we're going to finish. Let's go ahead and finish the chapter we were on. Chapter 15? Yeah, let's do that. Did you have a question?
Well, are we multiplying the absolute value and square root in the shortcut formula?
Yes. So in the shortcut formula, the question was, are we multiplying? Technically, yes. There's little times right there. Yeah, we're multiplying. And then we're multiplying here, too. I always see the mistake people add the fractions inside the square root. So honestly, knowing the formulas is like, I feel like that'll get you at least a 50% on the exam. Okay, so we did a bunch of examples. I feel like we did all these. Let's go to the next page. There's one last part of chapter 15 that is, okay, so it kind of combines what we learned about the formulas with how does that translate into real life. So the question is, what happens the more times we do something? Do I get more air or less air? Because eventually in chapter 17, so all next week, we're going to talk about surveys, sampling, polls, etc. And so this idea of the law of averages is going to come up in polls because you want to be as accurate as possible. And so it kind of makes sense. If I want my survey to be as accurate as possible, I need to sample as many people as possible to get as many different perspectives. So we can see that with the law of averages. So the law of averages is really similar if you've heard of the law of large numbers. It's kind of the same thing as that. The law of averages basically says that as n increases, the closer the average is going to be to the true average, and then the farther the sum is going to be to the true sum. So the law of averages is kind of complicated, to be honest. This sounds a little crazy, but if I write it here, let's write it in just plain English. It's saying as n increases, our standard error for the average decreases. Okay, so as n increases, your standard error for the average decreases, which means your average is going to have less error. And same with percent. My standard error for the percent also decreases. And for the sum, the only other one is the standard error for the sum. That actually increases. So as n increases, the standard error for the sum increases. And we can easily see that, mathematically speaking, if we look at all of those formulas that I just wrote down, right? We can see, here are my formulas. If I'm just looking at the standard errors, as n gets bigger, standard error for the sum gets bigger. And then for average and percent, as n gets bigger, standard error gets smaller. So the law of averages is really just a fancy way of saying exactly that that's what's going on. So we can model these types of questions. We can do a couple examples. So what does it say over here? It says, if we draw 100 times as many as we originally did, n is going up by a factor of 100. So if n increases by 100, what happens to our standard error? Well, we know it's going to increase, but it's not going to increase by 100. Instead, it's going to increase by the square root of 100, which is 10, because all of our standard error formulas have the square root of n. So it's the idea that as n goes up by 100, standard error goes up by the square root of 100. And then for averages and percents, the standard error actually decreases by a factor of square root of 100. Or I can say it changes by a factor of 1 over 10, because it gets smaller. So let's see, what's another good way to explain this? With coin flips, I've researched the law of averages a lot, because it's honestly, when I first started teaching Stat 100, I was like, this is so hard to teach. It's maybe not as hard to understand once you get it, but to teach it, it can be kind of confusing. So all the examples I looked at used coin flips. They said, if you flip a fair coin, you're likely to get closer to 50% heads the more you flip, but you're less likely to get exactly half heads. And I think that really stuck with me, because if I think about flipping a coin 10 times, getting exactly 5 heads is pretty probable, right? That seems totally reasonable. But if I flip a coin 1,000,000 times, getting exactly 500,000 heads gets less likely. There's more error the more you flip for the sum, if you're adding up how many heads you get. But for percentage-wise, for percents and averages, the error actually goes down. So the more you flip, if you're looking at the percent or average, the closer the average is to the true average. So let's do some examples. I think this will help. The next page, we'll come back to these, but I want some space. These have a bunch of writing on them. I just want to do an example with no hints or anything. Just how do I do it? So example 4, there's 4 parts, A through D, and this one says, in tossing a fair coin, fill in the blanks to make the chances equally likely. So I want to make I'm given 2 scenarios, and I want to make them have the same probability of occurring. So here's the first one. It says 8, give or take 3 heads, and 16 tosses is about as likely as 32, give or take how many heads, in 64 tosses. So they're telling us if I toss a coin 16 times, I'm expected to get 8 heads, give or take the standard error is given, it's about 3. So I'm expected to get 5 to 11 heads. How does that change if I toss the coin more? So if I increase n to 64, well, for the expected value, I still should get half heads. So the 32 makes sense. That's just the expected value when flipping a coin. We don't need a formula for that one. We can just, with a coin, it's super easy. You expect half. But the standard error maybe isn't as obvious of what it should be. So they want us to fill in the blank with the standard error to make the 2 scenarios have the same probability. So what I always like to do is write this out. I have 8 plus or minus 3 heads in 16 tosses is my first scenario. So this is my n, this is my expected value, this is my standard error. right? Because I could say I'm expected to get 8 heads, but as we've said in the past, it's better, flipping a coin, there's randomness. It's better to give a range. So how does that change if I do 64 tosses? Well, my expected value, I'm expected to get half heads, so still half, which is 32 in this case, in 64 tosses. And so I can use the law of averages to say, what does the law of averages say? I know n is going up, right? From 16 to 64, n is increasing. And the law of averages says as n gets bigger, this is what happens to the standard error. So I have to decide, am I dealing with sums, averages, or percents? And the nice thing is, since I'm counting up how many heads I get, I'm going to deal with sums for this one. If we were dealing with averages or percents, you'd see the word average, or like part B. Part B, I can say, I know I'm dealing with percents in this one, because there's all these percent signs. So if there's no mention of average, no mention of percent, we can assume we're dealing with sums. So for sums, if I look at the law of averages, it says as n gets bigger, the standard error for the sum gets bigger. So I know my standard error is going to increase. So this fill in the blank is going to be bigger than 3. Law of averages says as n gets bigger, the standard error for the sum actually gets bigger as well, and we multiply by the square root of n. In the formula, we take the SD and multiply by the square root of n. And the SD isn't changing because we're flipping a coin, so the SD is going to be the same no matter what. So I know that n, I can say 16 times what gives me 64, or do 64, divide by 16, and I get n is increasing by a factor of 4, which means my standard error is going to increase, not by 4, but by the square root of 4, which is 2. And visually speaking, I can see, oh, well, if the standard error increases by a factor of 2, it becomes 6. And now these two things, they have the same probability of happening. So I'm gonna say it one more time just in case anyone missed it. We said n is going up by a factor of 4, right? 16 times 4 gives me 64. So in our standard error formula, and what the law of averages said is that if n gets bigger, the standard error for the sum gets bigger. So I'm going to multiply my standard error, not by 4, but by the square root of 4 because of the square root in the formula. So we're just looking at, as one part of the formula changes, as n changes, how does that affect the thing we're looking at? So I could fill in my blank, let's see, 32 plus or minus 6. 32 minus 6 would be 26, and then 32 plus 6 is 38. So getting 5 to 11 heads in 16 tosses is just as likely as getting 26 to 38 heads in 64 tosses. Question, yeah? So because we're dealing with standard error, all of the standard error formulas, every single one we learned, we're not multiplying or dividing by n, we're multiplying or dividing by the square root of n. So if n goes up by 4, the standard error changes by the square root of 4, which is 2. Does that make sense? Okay, let me think of another way to explain it. I mean, you could test it out with like just plugging in numbers too, here, let's do this. Let me move this. Okay. So let's say our standard deviation is 1. Okay. And n is, let's say n is 10. And we increase by a factor of 4. So in my first scenario, so I have scenario 1. And then I have my second scenario, the SD is going to stay the same, and n increases by a factor of 4. So n would be 40, right? And then here's scenario 2. So if I found the standard error for the sum, in scenario 1, I would do, it's the square root of n times the SD of the box. So I would do the square root of 10 times 1. And then if I did scenario 2, I would do the square root of 40 times 1. So the only thing that's changing is, and then if I figured this out, let's see, this is a bad example because it's going to be a decimal, but the square root of 10 times 1, let's see, is, square root of 10 is 3.16, and then the square root of 40 times 1 is 6.32. So n went up by a factor of 4, right? 10 times 4 gives me 40. And the standard error only went up by, this times 2 gives me this. It only went up by a factor of 2 because of the square root of n. If the formula was n times the SD, then sure, we'd multiply by 4. Then it would be a direct relationship. But because it's the square root, then we have to take the square root. If you still have questions, talk to me after class. But does anyone have any other questions? Maybe let's do another example. This is something that I've realized people don't do. Like, this isn't something that I've heard of people doing in high school, like saying, as something in the formula changes, how does that affect the outcome? So maybe let's do this one. Maybe this will help. Doing a second example. So we have two scenarios. 50%, give or take 20% heads in 16 tosses. Is about as likely as 50%, give or take blank heads in 64 tosses. So this is, okay, so n we know still is increasing by a factor of 4. So n's going up by a factor of 4. And all of these other numbers, what they tell us is, okay, if I toss a coin 16 times, I'm expected to get 50% heads. These are still expected values. Give or take 20%, so that's given. And it doesn't matter, even if I toss a coin 64 times, I'm still expected to get 50% heads, right? If I toss a coin a million times, I'm expected to get 50% heads. So that's why these two are the same. Here, I'm actually counting how many heads I get, so I'm expected to get half heads, whereas with percents, you're always expected to get 50% heads. So if n goes up by a factor of 4, for percents in the formula for standard error, I don't multiply by the square root of n, I actually divide by the square root of n, right? And if we just look at the formula, let's see, here, we can look at it. Hold on. It is, I just wrote it. It is right here, standard error for percent. We divide by square root of n. So if I just divided by n in the formula, I could say, oh, we just divide by 4. But because I divide by the square root of n, this isn't going to change by 4. It's going to change by the square root of 4, which is 2. So my new standard error is going to get smaller for percents because we're dividing. So if I look back at the law of averages, it says as n gets bigger, the standard error for the percent gets smaller. So this is going to be, I'm going to divide, again, not by 4, but by the square root of 4, which is 2. So I get 10. And then let's see, so 50 minus 10 is 40. 50 plus 10 is 60. So getting 30 to 70% heads in 16 tosses is just as likely as getting 40 to 60% heads in 64 tosses. So the moral of the story is, as n gets bigger, our standard errors change by the square root of n because of the square roots in the formula. For sums, we multiply. For percents and averages, we divide, is the deal. So we're going to check if you guys, we'll see if you guys are on the same page as me, and if not, we'll do a couple more examples. But I'm going to ask you guys a couple questions. So I forget which one I have, so I'll let you guys know in a minute. N is increasing by, which one is this? Okay, it is, so the one we're going to do, so ignore all of this writing. The one we're going to do is oh good, there's not a bunch of stuff here. Part C on the previous page. So on page 133, we're going to do part C. So the first step is always saying, n, what is n increasing by? So for part C, on page 133, we're going from 20 to 2,000 tosses. So first question is, n is increasing by a factor of what? So I'll let you guys answer. We'll take a look. Okay, so we're just doing step one. So we're just saying n is increasing by a factor of what? We're not finding the new standard error or anything yet. So hopefully everyone has responded. Go ahead, click your answer. No, not yet? Not yet, okay. Okay, go ahead and answer even if you have not yet. Let's check. N is increasing by a factor of... Yay, okay, good. You guys are on the same page with me about that. 100, right? N is going from, here we go. Let's go back. That was good. 20 to 2,000. So 20 times what gives me 2,000? You could do 2,000 divided by 20 to get that answer. So I set this up, I really like setting it up like this, because visually you can see exactly what's going on. So this is saying if we toss a coin 20 times, we're expected to get 10 heads. Give or take 2 is the standard error. If we toss a coin 2,000 times, we're expected to get half heads, 1,000 heads. But what should I put as the standard error? So my next question is, all right, part 2. The next question says, this means, so n's going up by 100, what do we do to our original standard error? So I have to do something, if I go back to this, I have to do something to the 2. I have to change it, because n is changing. So the question is, do I multiply, do I divide, and by what? So back to, sorry, I keep going back and forth. I'm going to go back to the question, what do we do to the 2? So I'm not asking what number do I put here, I'm just asking what do I do? How do I get that number? Oops, nope, not that one, this one. Here we go. So are we multiplying, are we dividing? And by what? Oh, good, okay, you guys are doing good. We're gonna multiply because we're dealing with sums, right? No mention of average, no mention of percent. And then because of the square root in our formula, we're gonna multiply not by 100, but by the square root of 100. Okay, good. And then my last question is, what do I put in the blank? What is my new standard error? What is the standard error that will make the 2 scenarios have the exact same probability? So what is the final answer is the question. Okay, finally, what is my new standard error? Let's see. So we said in the previous part, we said we were going to multiply by 10. So the question is, what do we multiply by 10? D, that looks great. All right, so like 85% of people seem to be on the same page. So exactly, we said we're dealing with sums, n goes up by 100, standard error goes up by the square root of 100. If we're dealing with percents like this one down here, I have, let's see, 50%, give or take 10% heads in 20 tosses is about as likely as 50%, give or take how many heads in 80 tosses. So here for percents, the law of averages says that as n gets bigger, the standard error for the percent actually gets smaller. So the only difference between these two is here, instead of multiplying for percents, we're always going to divide. And still by the square root of n, not by n. So in this one, we can see n is increasing by a factor of 4. Which means we said for percents, we're actually going to divide by the square root of 4, which is 2. So this should be 5. So now these two things have the same probability of occurring. So I would recommend when doing these types of problems to just go ahead and write it out like that. If you're a more visual person, I think it helps. N goes up by 4. Standard error changes by the square root of 2. And the question is just, are you dealing with sums, averages, or percents? For coins, averages are kind of weird, so you'll notice we don't even have any examples of averages. But averages are just like percents. We divide by the square root of n. So that was good. We'll do one more, and then I promise we'll be done with this. But just to make sure, which one should we do? Let's do, maybe this one's a little more complicated. It says 4 give or take 1 heads in 8 tosses is about as likely as 576 give or take how many heads in 1,152 tosses. So this one's just a little weird because the numbers are so strange. But my first step would be to say, okay, n is increasing by a factor of what? 8 times what gives me 1152. And I don't know that off the top of my head, so I would just use, well, I secretly already did it. Yeah, I would just do 1152 divided by 8. Can you guys see that? It's kind of blurry, but it's 144. So n is increasing by a factor of 144. So 8 times 144 gives me 1,152, which means my standard error, I have to decide, am I dealing with sums or percents? So what do you guys think? Sums or percents? Sums, yay. Okay, good. Sums, so that means I'm going to multiply. My standard error is going to get bigger. If you're ever confused, do you multiply or divide? You can just look back at the formula for standard error and check. Do you multiply by the square root of n or divide? Or in your homework, you can come back to here and look at the law of averages and say, oh, n's getting bigger, standard error for the sum should get bigger. So I am going to multiply, yeah. Not by 144, but by the square root of that, which is 12. So 1 times 12 is just 12. And there we go. Done. Yeah.
So in this problem, what is the plus or minus 1 head? Like, is that, like, why are we multiplying the 1 by the 12?
So in this problem, what are all the numbers is the question. So 8 and 1152 are the number of tosses, right? Those are my n's. 4 and 576 are my expected value. So if I toss a coin 8 times, I should get half heads, right? I should get 4 heads. If I toss a coin 1,152 times, I should get half heads. So 576 is just half of this. And then the give or take, the after the plus or minus, that's my error. So like every time, if I toss a coin 8 times, if all of us did it in this room, sure, some of us will get 4 heads, but some of us might get 5 or 6. I guess some of us could get all 8 heads. It just depends. So that's the standard error they're giving me. And then I want this standard error to make it so that these two things have the same probability. So expected value plus or minus standard error is the deal. So that's the law of averages. You guys will get way more practice with this on the homework. And then I'll kind of come back. We skipped a couple examples. I'll probably do this on Thursday just as a refresher. But for now, I feel like we've done a bunch of these. We've done enough. Let's go to our next chapter, which is chapter 16. But yeah, if you guys ever are skeptical of something too, you can just try it out with numbers and see what happens. That's a good way to check. But if anyone still has questions on the law of averages, it is kind of confusing. So just talk to me at office hours or after class. We'll figure it out. But okay, so we're moving on. The next chapter, so before we start talking about polls and surveys and all that fun stuff, there's one more thing that we have to cover, which is probability histograms. And this will be good for you guys. You've already done histograms. We know histograms pretty well. So the question is, how do we make an adjustment for random variables? So it says back in chapters 3 and 4, Right here, back in chapters 3 and 4, exam 1, we summarized a list of numbers by the average, SD, and then looking at a histogram. Right? We did that. That was exam 1. You guys had to read and draw histograms, do all that stuff. In this exam, exam 3, now we're looking at random variables. So we summarize random variables by expected value and standard error, right? Here, let's see. So it says in chapters 14 and 15, we summarized numbers generated by a chance process by the average and expected value. So now we're going to do a histogram kind of just like we did before. And I actually think that probability histograms are maybe even a bit easier to understand than regular histograms. Regular histograms have that confusing y-axis. That's the density, it's the percent per point, and it's not intuitive on what exactly that is. But with probability histograms, the nice thing is the x-axis is always just your possible outcomes. So your x-axis is going to be all the possible outcomes of your chance process, and the y-axis is just the probability. So it's super easy to interpret. What's the probability of X? So our first example, maybe I should write that. Yeah, let's write this over here. So the x-axis is always all possible outcomes. And then the y-axis is just the probability. It's the probability of each outcome. Okay, so if we're just doing something once, it's really easy to think about what are the possible outcomes, what are the probabilities. It's when we do it more than once that it gets a little more tricky. But let's start off with an easy example. It says, what's the probability histogram for rolling a single die and counting the spots? So the spots, that's going to be our random variable, right? That's what changes. Random variable. So if I was going to draw my box for a single die, I know that there are going to be 6 outcomes. So there's going to be 6 tickets, and they're just going to be how many spots there are. So 1, 2, 3, 4, 5, and 6. So if we said counting the number of 2s, we did that one last week where we said, okay, the 2 would be counted as a 1, everything else would be counted as a 0. If we're just looking at, yes, we got a 2, no, we did not get a 2. But here we care about the spots. So if I get 6 spots, I want to count that as 6. So kind of a review of box models. And then for my probability histograms, my outcomes are just 1, 2, 3, 4, 5, and 6. And so the outcomes are all those numbers, and then the probability is just the same for all of them, right? The chance of getting any of these is 1 out of 6. So my probability histogram is going to look super boring. Here's the first bar, here's the second bar. All the probabilities are exactly the same. So this is a nice uniform distribution. It doesn't look super exciting, but it gets the job done. It tells us what we want, that there are 6 outcomes, they all have the same probability. So we drew this probability histogram for one draw, or one roll. In other words, n equals 1. On some of the practice exams, sometimes you'll see this wording, I'll say draw the probability histogram for the contents of the box. For the contents of the box. And that just means the exact same thing because we draw our box for one single draw, right? We always draw our box for one draw. So those mean the exact same thing. But I'm going to highlight this because last semester a bunch of people asked me what this means. But it really just means for one draw. It's the same exact thing. So that's basically it. With a histogram, we want to think about 2 properties that I talked about. One is that the total area, The total area is always equal to 100%, or in this case, 1, if you're dealing with fractions or decimals, right? That applied to a regular histogram. That also applies to a probability histogram. And remember this, too, that the x-axis is drawn to scale. I think there were a couple other things we talked about with histograms, but all of them still hold true. The only difference is basically just what's on the x and y axis. So that's for one draw. Not too bad, right? Let's think about what if we wanted to do it for 2 draws. So it says, what's the probability histogram for rolling a pair of dice? So in other words, 2 dice, which means n is equal to 2. So it says we can think of, if we're thinking in terms of a box model, I would definitely draw this box. I would say, let's draw the box for 1 draw. So it would be the same box as above. We'd add 6 tickets. And then I'd just draw twice out of here. So I would say, here are all my tickets. Oops, I ran out of room. There we go. And I would say we would draw from this box, draw n equals 2 times, and then I'd draw with replacement, right? Because if I get a 1 on my first roll, I can get a 1 on my second roll. So this is how we have done this in the past, right? This is what we did all of chapters 13 through 15. And that's good when we're calculating expected value and standard error, but when we're drawing a probability histogram, I have to actually think about all the options, right? Because if I think of all the possible outcomes, I technically can get anywhere between the smallest I could get is 2 1s, the smallest sum I could get is 2 1s, the biggest sum I could get is 2 6s. So my possible outcomes, it says there are 2 to 12 as my possible outcomes either way. So if I drew the box just for rolling 2 dice, which I don't really recommend, but I'll draw it just so you guys can see all the outcomes, I can get a sum of 2 all the way to 12. So here's 5, 6, 7, 8, 9, 10, 11, and 12. So this is if I roll 2 dice, or 1 die twice, it's the same thing. And we know that there are going to be 36 options. So 36 tickets. And then I would have to think about, this doesn't look like there's 36 tickets, so I'd have to think about, like, how many ways are there to get a sum of 2? Well, I can get a 1 and a 1. There's really only one way for that to happen if I'm rolling 2 dice. For a 3, to get a sum of 3, we've done this before, right? I can get a 2 and a 1 and a 2. So there's 2 options. I could look back at that picture at the beginning of chapter 12 to see all these. To get a sum of 4, we've done this as well. I can get a 3 and a 1 and a 3, or a 2 and a 2. So there's 3 different ways to get a sum of 4. And then I could go ahead and do that for all of these, but that would take forever, so I'm just going to give you guys the lowdown. Basically, 7 is the most probable outcome, and then it goes down from there. 5, 4, 3, 2. There's one way to get a 12, right? I can get a 6 and a 6. So this isn't really helpful for anything besides drawing the probability histogram, because now I can say, all right, I cannot get a 0. I know that. If I roll 2 dice, there's no way I could get a 0. There's no way I could get a 1, but I can get a 2. So the chance of me getting a 2, a sum of 2, would be 1 over 36. So my outcome's 2, my probability is 1 over 36. My chance of getting a sum of 3 is going to be 2 out of 36. And then I could go ahead and draw this thing. The peak is at 7. 7 is the most likely outcome. So if you're ever playing a game that involves rolling 2 dice, bet on a 7. Or like if you need to say if the next person's going to roll higher or lower than you, I always think about that. 7 is the most probable. Okay, and then the rest of it is very similar to the other side. It's nice and symmetrical. There we go. That's not the prettiest picture, but it looks relatively like the normal curve. So this is, and I wouldn't expect you guys to draw this on your own because this is complicated, but it says to draw the probability histogram for the sum of two dice. So disclaimer, that will not be on the test. You won't have to draw this on the test, but that's where it comes from. And then if I do 3 draws, if I roll the die 3 times and take the sum of my dice rolls, my histogram is going to be even more complicated. I'm going to have to do even more outcomes and more probabilities. So instead, what I usually do is just use a computer program to generate these histograms. So here is the exact same histogram. Below is a histogram for rolling 2 dice, rolling a pair of dice. And this was generated by our data program. You could use any software to generate a histogram like this. And it's the same thing. Here are all my outcomes, 2 through 12 spots. And then the density is just another way to interpret it is the probability. And this one looks better than the one that I drew, but it's really the exact same thing. So if you guys ever want to do any of these simulations or like double check your work on the homework, we can go to, so if you go to our Stat 100 website, because this class, I don't expect you guys to do any programming. That is not in the syllabus. So we don't learn like any programming languages, but our data program lets us just point and click, which is really nice. So if you go to our website and then go to data program, usually we click on data analysis program to see the survey. But instead, there's an option called simulations. So I can go ahead if let's see, I'll show you guys how to get there. But we can actually simulate doing what we just did. So let's get out of here. Oops. Here we go. So here's our website. Google Stat 100, we're the first link that comes up. And then here is data program. And then usually we click on the first one, but I'm actually going to click on the second one. And then depending on what you're looking at, we were looking at probability histograms of sums, right? Because we were adding up how many spots we got. And I can put as my box, the nice thing is you can just put your box for one draw. So for a die, 1, 2, 3, 4, 5, 6. So there's my box. It looks good. And then if I press go, it actually gives me the probability histograms for one draw. So here, right here, this one, that's the first one we drew. This 2 draws, that's the second one we drew. And then you can see the more draws I take, the more crazy my histogram gets in terms of there's a bunch of bars. I don't want to draw that. That's going to take forever. So on the exam, if I give you guys a probability histogram, I'll probably have gotten it from the data program. And we can see, let's see, rolling a die 100 times right here. My probability histogram looks like our best friend, the normal curve, right? That looks like a normal curve. So that's not a coincidence. So actually on the very next page, there is a theorem. I think this is the only theorem I talk about in this class. But it's the most important theorem in statistics. One of the most, I should say. And it saves us so much time. It's called the central limit theorem. So it says the probability histogram that we created for 2 draws looks like a bumpy version of the normal curve. And if we saw that as we did 3, 4, 5, all the way up to 100 draws, the histogram looked closer and closer to the normal curve. So that is this theorem, this central limit theorem. It wasn't a coincidence that happened. So the abbreviation for central limit theorem is the CLT. Sometimes in papers, they'll refer to the CLT. It's like, what is that? It's the central limit theorem, which basically says the probability histogram for all sums, averages, or percents will get closer and closer to the normal curve as n increases. So it's saying as n goes up, as n increases, the probability histogram gets more normal. The probability histogram gets more normal. So basically what we can say is, let's not worry about drawing our own probability histograms, because if n is big enough, we know that our histogram is going to look like the normal curve. And we can see that for any scenario, any random variable. It says this works for, I should even highlight this works for sums, averages, and percents, which is what we've been dealing with in Stat 100. It doesn't work for products or anything other than sums, averages, or percents. But it's super nice. So if let's see, if I think about, I don't know if we have to do all of this, but let's see. So if I have flipping a coin, it says draw the probability histogram for the number of heads in 1, 2, 3, and 4 tosses of a fair coin. So one toss, so here's my box model. I have 2 tickets. We've done the coin before, right? The random variable is the number of heads. So I can easily do this for one toss, right? If I toss a coin once, I can either get 1 head or 0 heads, head or tail. So for my probability histogram for one toss, down here, the number of heads, I can either get 0 or 1. And then and then both of these have a probability of 1/2, right? So here is my probability histogram. So it looks kind of boring, nothing too crazy. There's 2 options. Each of them have 1/2 probability. But if I toss a coin 2 times, it's not as complicated as the die, but here are my possibilities. So with one flip, I have 2 possibilities. With 2 flips, here are all my possibilities. Right? So I can think of this, I can say, all right, this is 0 heads, this is 1 head, this is 1 head, this is 2 heads. And I could do the same thing. Here are all the possibilities for tossing a coin 3 times. Here are all the possibilities, there's so many, for tossing a coin 4 times. But if I draw these probability histograms, so here what they're doing, they're saying, okay, toss 1, I can either get a head or a tail or a head, and toss 2, I can either get a tail or a head, and then come up with these 0, 1, 1, and 2. I can say, okay, if on toss 1 I get a tail, I get no heads, and on toss 2 I get a tail, that's a total of 0 heads. If on toss 1 I get a head and toss 2 I get a tail, that is a total of 1 head. And then, etc. If I get a tail on toss 1 and a head on toss 2, that's also a total of 1 head. And then if I get a head and a head, that's a total of 2 heads. So for n equals 2, I can say I can either get 0 heads, 1 head, or 2 heads. And if I toss the coin twice, I should get 1 head is my expected value. So the chance of getting 0 heads, there's 4 possibilities, and there's 1 way to get 0 heads, right? Here I have 4 possibilities. Here they all are. 0, 1, and 2. So the chance of getting 0 heads is 1 out of 4. The chance of getting 1 head is 2 out of 4. And the chance of getting 2 heads is just 1 out of 4. So I can see, it says, as the number of tosses increases, do the histograms look more and more like the normal curve? Sure, I could draw for 3 and 4, but it looks like yes, right? This looks more like the normal curve than this. If I go to our data program, we can double check this. So my box is just 0 and 1 for a coin. And if I press go, I can see here's 1 draw, 2 draws, 3 draws, 4 draws. The more draws I take, the more and more, looking good, 100 draws, the more and more the histogram looks like the normal curve. This one might even need a few more to look smooth, but you can see as n gets bigger, the histogram looks closer and closer to the normal curve. So that's the central limit theorem. It doesn't matter what I put in here. I can put 0, 3, and 100. As long as we're dealing with sums, averages, or percents, let's press go. So here's the probability histogram. They, at first, don't look like the normal curve at all, but as n increases, let's keep going, you can see they're kind of forming into this nice normal curve, which will happen no matter what. So that's saying all the possibilities on the x-axis, all the probabilities on the y-axis. As n goes up, the histograms look more and more like the normal curve. So to answer this question, as the number of tosses increases, do the histograms look more and more like the normal curve? I'm going to say yes. That is the central limit theorem. So there's one more example I want to do, and then we will be good. Okay, this is saying you can look at the data program. But here's the central limit theorem again. It says, regardless of what the original box looks like, with a large enough number of draws, the probability histogram should follow the normal curve quite closely. But the question is there a magic number of draws that I can say, all right, once we hit this number, once we get to 100 draws, I know the histogram is going to look normal? And that actually depends. It says how many draws is large enough. It depends on the original box. So basically, the more the histogram of the contents of the original box looks like the normal curve, the less draws you need. So the more the original box looks different from the normal curve, the more draws you're going to need. So here's a really good example of this. There's box A and box B. So box A looks there's nothing weird about it, right? 1, 2, and 3. If I decided to draw the histogram for the contents of each box, that means for n equals 1, that means if I draw one time out of box A, I know I can either get a 1, 2, or a 3, right? And the chance of all of those is just 1/3. So here's my probability histogram for one draw. And this doesn't really look like the normal curve, but it's not weird or anything. It's just a nice, normal, uniform histogram. So I would call box A a relatively normal box. There's nothing weird about it. Everything's equally spaced, 1, 2, 3. And then if I drew the probability histogram for 2 draws, it should look closer to the normal curve. But box B is kind of weird. I have 1, 2, and 9. So if I were describing these two, I would say box A looks normal. There's nothing weird about it. Box B is a bit lopsided. Okay, box B is a little lopsided. And the deal is that the lopsided boxes need more draws to look normal. All right, so the more normal, and by normal I mean there's just one of each of the numbers, they're one away from each other. Lopsided, there's either a bunch of ones or there's 1, 2, and 9 is really far away. That's what I mean by lopsided. So box B, if I was going to go ahead and draw the histogram for one draw, I could either get a 1, 2, or a 9. And I have to make sure to draw the x-axis to scale. So I got to go all the way out here to a 9. And there's, again, a 1/3 chance of getting any of those options. So I can either get a 1, a 2, or a 9. So box B definitely doesn't look normal. It has this big space in between. So we can kind of see if we go to 2 draws, which was box A and box B, it's not super horrible. On 2 draws, it says now draw the probability histogram for 2 draws. So n equals 2. So that means we can get the smallest sum I can get is 1, 2 ones. Biggest sum I can get is 6. So if I think about here's draw 1, I just want to list out all my possibilities. Here's draw 2. And I can get a 1 on both, right? I can get a 1 on draw 1 and a 1 on draw 2, so my sum would be 2. Or I could get the extreme, a 3 on draw 1 and a 3 on draw 2, so my sum would be 6. And then there's 9 possible sums, so I want to fill all of them in. 9 possible sums. So I could get a 2 and a 1, which would be 3. I could get a 3 and a 1, which would be 4. So I'm just adding together the 2 numbers. Let's see, I could get a 1 and a 2, which would be 3, a 2 and a 2, which would be 4, a 2 and a 3, which would be 5, etc. So here are my 9 possible sums. And I could do the same thing for box B. Box B still has 3 tickets, so I'm still going to have 9 possible sums. But my sums are going to have a different range. For draw 1, I can get a 1, 2, or a 9, and same with draw 2. And then I could get a 1 and a 1, which would be a sum of 2. Or the most extreme is I could get a 9 and a 9, which would be an 18. So my sums range from 2 to 18. There's a bigger range. I could get, let's see, 3, 10, what are all these? 3, 4, 11, 10, 11. So here are my 9 possible sums. So if I was going to draw these, let's do this one first. There's 9 possibilities. There's 1 out of 9 ways to get a sum of 2. Right? There's 2 ways to get a sum of 3, so 2 out of 9. How many 4s are there? 1, 2, 3 ways to get a sum of 4. And then there's 2 ways to get a sum of 5 and 1 way to get a sum of 6. So I can see that box A looks pretty normal. After only 2 draws. So after just 2 draws, I see the central limit theorem in action with box A. This original histogram right here to this one, we're definitely looking more and more like the normal curve. Let's see if the same thing happens for box B. So there's a 1 out of 9 way to get a 2. 2 out of 9 way to get a sum of 3. 1 for the sum of 4. And then we skip, there's no 5 all the way through. The next number is 10. So there's a 2 out of 9 chance of getting a 10. There's also 2 11s. And then there's 1 18. So box B, I'm going to say box B does not look normal. It doesn't look normal at all. It was lopsided originally. It's lopsided and needs more draws. So the central limit theorem says it'll eventually look normal, but after 2 draws, it doesn't look normal. It definitely needs more draws. So the central limit theorem holds, but we need more draws for lopsided boxes.